Hi there, Philip from Minecode here. In this video I will be explaining how detection works under the hood. In my last YouTube video I was explaining the implementation of a detection functionality, so if you are interested into the implementation, you can check my previous YouTube video. You can find also link in the description. You will be implementing there the actual implementation of this detection. This lecture is just about the explanation of this if statement, how you can check if the player is in this angle here, in this detection range of the enemy. Okay, so with that said, we can start. I hope you have your project, so you can find also the projects in this previous YouTube video, also link in the description. You can run this project. And the first thing what we'll do, we'll just simply change the enemy and the player position, so it's easier to imagine this, or also easier to draw it on the paper. So simply I will place the player enemy here and the player on up here like this, and I will change the enemy angle to 180 degrees. So if enemy is facing actually not this, but the enemy, I'll change the enemy to 0 degrees, so enemy is facing the player. Okay, and the player will have a click on the player, and the player will have a 0 degrees on the, or actually 180 degrees, so it's facing the enemy like this. Okay, so what I would like to do, I would like to imagine these positions and the enemy and the player on the 2D grid. So you can place here this top to bottom view. Okay, so just place the camera somewhere up here. You can imagine this 2D grid like this. So in Unity, you have an X and a Z axis, and they look like this. So you have a Z axis here and X axis here. So this is your X axis and this is your Z axis, and each game object is on specific position. So here is on position, also here is on position, and here is a starting 0, 0. Now we'll mark it exactly in to the grid. I have prepared in a Photoshop, so you can just sit comfortable and you can watch. All right, so let's imagine I will change the color to the red so it's more visible. All right, so as we had it in our game, let's say our enemy is somewhere. Let's say enemy is here. All right, enemy is here. And let's place the player actually somewhere close to the enemy, so it's easier to imagine this. Or let's place the enemy player. Let's see, let's click on the enemy. Let's place the player somewhere in this detection range. Okay, so let's say here. Okay, let's say here. I will just verify it's yes, I'm in the detection range of the enemy. Okay, so here, if I will illustrate it here, enemy, the player can be somewhere. Let's say player can be somewhere here, right? So let's mark the player somewhere here. This will be my player. Okay, so I'll mark the position somewhere so I will not forget them. So let's write here enemy position is at 2, 1, 2 on the X, 1 on the Z. I will mark here also axis, so X and the Z. Okay, so here is my enemy and the player. Now it will be harder to get the player position. So let's say 2.2, 2.4, 2.6. So 2.6 on the X axis. And on the Z, this looks like yeah, 3. Okay, that's a 3 on the Z. All right, so we have our positions. We can also mark here the detection angle. That's a 45 degrees. 45 degrees should go somehow like this. It should be 45. And the 45 to other angles. So we have a detection angle of a 90 degrees in the total. It should be like this. All right, so let's say take a look on the equations here. So first we are getting 2-player position. That's a position from the enemy to player. 2-player position you are getting with the player position minus enemy position. Okay, so we'll get here. I'll mark here as the 2-player position. I will say here TP position. That's the player position minus. That's the player position minus enemy position. Okay, so TP position will be player is a 2.6 minus 2. That's a 0.6. 0.6 on the X and on the Z, that's a 3 minus 1. That's a 2. Okay, that's a 2. Okay, so if I would like to go from the enemy to the player, I need to go 0.6 value on the right side. So I need to go 0.6 here, and I need to go 2 values up here, and this will get me player position. That's this position here. Okay, that's what this vector is saying. So that's this vector here, basically, this vector here. This is the vector we are looking for, 2-player vector. What's happening now, we would like to transform this vector into the normalized vector. What does it mean to have a normalized vector? This vector here has some magnitude, and this magnitude has some length. This length here, as you can see here, when the position is 0.6 and 2, it's definitely longer than 1. Normalized vector has a magnitude always 1. Okay, so if you have a normalized vector, you will keep the direction of your vector, but you will either scale it up or scale it down. So magnitude of this vector, length of this vector will be 1. Okay, so this is definitely longer than 1. You will just simply scale it down, so it will have some positions, same direction, but the magnitude will be 1. So the vector can be somewhere here. Let's say. I don't know exactly what position should be if that the length of the vector will be 1. We can find it out, okay? Okay, so here I will mark this is our 2-player position. All right, this is our 2-player vector here. We would like to scale it down now. So 0.6 and a 2, you can put it to Omni calculator, for example. Let's look here for, I just search in a Google normalized vector online, and let's go here to Omni calculator, and let's place these values here. So for the X, we set 0.6, and for the Z, which is Y, in this case, we get here, let me verify it, 0.6 and 2. Okay, 0.6 and 2. You can see the magnitude of this vector is 2. So if you want to scale it down, the position of the X and the Y will be 0.28, 29, and 0.95. What we can do now, that we know the scaled versions of this vector, we can actually imagine everything on the unit vector. So this position here of the enemy 2, 1, we can translate it on the unit vector here, on the unit circle. Unit circle just simply means that the radius of the circle is exactly 1. Okay, so I can imagine now that the enemy is here. Okay, that's my x-axis. All right, and since this has only length of the 1, and I translated my normalized vector to player position, so this position here to the player, normally the player will be somewhere here, but since I had scaled it down, I had normalized it, I know the positions are now 0, 29, and 96. I'll write it down somewhere, okay? So our normalized, so TP normalized N is 0.20, okay, I forgot, 29 rounded, and 0.96, and 0.96. I can mark these positions now on my unit circle here. So X is 0.29. So here is, let's say, 0.5 and 0.29. Oh, hard to say, guys. I would say somewhere here, maybe somewhere. Okay, let's say somewhere here. So half of this should be 0.25, so a little bit larger. Maybe here. Hard to say. So this is a 0.29, let's say. Okay, and I will mark it here. So I'll mark here perpendicular line to this. And this will be actually 0.96, this position. This will be 0.96 position. Because I told you, this vector here, 0.29 and 0.96, has a magnitude of the 1, and the radius of the unit circle is 1, so this has to be 1. Okay, so that's a position 96 in order to be on the circle. Okay, so that's my player position when it's scaled down relatively to the enemy. Okay, that's I can mark here, player position is here. And now the interesting part. What I'm saying here is the dot product of two-player normalized, and the transform forward is larger than the cosine of the half of the angle of detection angle. Okay, so let's write here dot product now. Okay, so dot product here. All right, so we'll mark it here, dot product here of our normalized vectors. So our normalized vector of 0, 29, and 0, 96 dot product with transform forward. Transform forward is the forward vector of the enemy. Since enemy is here, transform forward is this vector here. You can see it's already marked here. That's the 0, 1 vector. Here, this vector here, 0, 1, x 0, z 1. That's a transform forward vector. In this case, when the enemy is facing the direction forward. Okay, so we know what's a transform forward, so that's the 0, 0, 1 in this case, and the dot product, you need to multiply each part separately, and then you need to add them together. So you are multiplying 0.29 and a 0, which makes 1, a 0, all right, and plus 0.96 multiplied by 1 is 0.96, right? So that's a 0.96. 0 plus 96 is this value here. Okay, so that's the point here of the player. We already found it. That's a dot product. Now we would like to we want to have this larger than the cosine of the half detection angle. Our detection angle of the enemy, you can see it here, is a 90 degrees. You can see it here, 90 degrees. So half of this angle is 45 degrees. All right, so we are looking for 45 degrees here. Okay, we don't know what the value actually is yet. Okay, we need to compute it. Okay, so if you want to know what the cosine of 45 degrees, just put it into calculators. Okay, so we are looking for let's play the calculator. I'm looking for the cosine of 45 degrees. All right, and that's a value 0.707. When you will round it, that's a 0.71. Okay, and that's the value here. This is a 0.71, so that's a 45 degrees. This is a 45 degrees here and a 45 degrees here. Okay, actually like this, I will mark it. You can see the value from the left and the right is exactly the same. Okay, on the right side of the circle, on the left side of the circle, these values on the circumference are the same. Okay? Okay, actually I can maybe use the different color. Let's use here again green. It's hard to see now. Okay, so that's the value here. The cosine of 45 is this value here. 0.71. 0.71. Okay, so my dot product, here we have computed of my two-player normalized, and the forward vector has to be larger than the cosine of 45 degrees. Yeah, and you can see that's right. My player is in a detection angle of this, because my player is here. My player is here. It's larger than this here, these values. Okay, so my player is definitely in a detection angle of the enemy. So that's why we are using these if statements, and that's why we are computing it is mathematically like this. Also, to verify the cosine of 45 is indeed here, we can also create from this right triangle. Okay, this is right triangle you can see here. And the angle of here is this 45. This is 45 degrees, this angle. Let's say this left part of the triangle, we can call it y. And the radius of it's a 1. Okay, it's a unit circle, the value is 1. So if you know trigonometry function, cosine 45 degrees. So cosine is what? That's the adjacent side divided by the hypotenuse. So adjacent side is this y we are looking for, and hypotenuse is 1. This is basically saying that the cosine of 45 is y. And we already computed was the cosine 45, that is the 0.71. This saying that the y is 0.71, and that's the value here on this unit circle. This is this value here. All right, and now you can imagine it really doesn't matter where the player is located how far is player located from your enemy. You can always translate player position on a unit circle, and you can compare the angle of the enemy angle with this position. You just need to get a dot product of the two player and the transform forward, and this has to be larger than the cosine of the half angle of the enemy. Okay, it doesn't really matter if the player is here, or the player is here, or the player is here. You're always getting this vector, and you're always just scaling it out. You're normalizing it, so its magnitude is 1. So you are projecting it always on circumference of the circle. This vector here, you will normalize to the circumference. This vector is smaller, you will normalize it to circumference, and so on. And then you will just get the angle, detection angle, and you will get this cosine. Okay, now it's not very visible, but yeah, we can. Actually, you can draw it on the paper on your computers. We will also try the different case. Okay, when the player is not in the detection angle of the enemy, let's say. Okay, but if you already understand this, you can also already finish video, but I will be showing the other case, which will be very similar what we have just drawn right now. Okay, so let's clear out everything. Actually, I will clear out this. We just keep here player position because the player position, enemy position will not change. Also, player position will change in this case. So I will remove these parts here. Also here, like this. And let's say in this case, the enemy angle, detection angle will be 180 degrees. So this will be the detection angle basically. This will be basically detection angle. This entire part here will be the detection angle of the enemy. So let's place the player somewhere behind this. Okay, somewhere behind this detection angle. So I will place the player, let's say, on the position here. That will be my player position. So my new player position is, let's mark it here. My new player position is x3, z0. Now we need to compute two player position. That's the player position minus enemy position. So 3 minus 2 is 1. And 0 minus 1 is minus 1. All right, so if I want to get from the enemy to player, I need to go 1 to the left and 1 to down. Okay, that's this vector. What does this vector say? All right, and actually you can see the magnitude is here. That's the magnitude of this vector. And the magnitude of this vector is definitely larger than 1. So we need to figure it out what the normalized vector is here of this 1 and minus 1. We can put it to here. So we are looking for the magnitude of a vector x1 and a z minus 1. Like this, and that's a 0.7 minus 0.7. We can also find it out mathematically through the right triangles, but I don't want to waste the time here. So that's the normalized this. So this normalized, we said it's a 0.7 and a minus 0.7. That's the normalized position of this. We can verify it one more time. Yeah, 0.7 and a minus 0.7. All right, now we can draw it on the unit vector. I can just change the colors. All right. Okay, so here, so 0.7, again, it's somewhere half here. 0.7 will be somewhere here. The 0.7 perpendicular line to it. Okay, that's a minus 0.7. Okay, so our player position is here, relatively to the enemy. That's a player position here. All right, and yeah, let's mark it. Now we need to get a dot product. So dot product of this position, so 0.7 and a minus 0.7 dot product with transform forward of the enemy. Transform forward in the enemy is in this case is 0, 0 and 1. Again, I'll show you one more case when the dot product will be when the transform forward will be different very soon, but let's keep it 0, 1. All right, so that's the x part multiplied by the 0. This will be 0. And the Z part will be minus 0.7. So plus minus 0.7, which makes me dot product minus 0.7. Okay, so dot product here will be minus 0.7, and this has to be larger than the cosine of half angle of 90 degrees. So half angle of half angle of 180 degrees, which is a 90 degrees cosine. So we need to find the cosine of 90 degrees. Okay, so let's find the cosine of 90 degrees. You will see that will be 0. All right, so that's a 0. Okay, so this value has to be larger than a 0. And you can see this condition is not met. 0 is here. This value is definitely not larger. This means the player is definitely not in the detection range of the enemy, because detection range of the enemy, you can also see it visually, is here. This 100. I can really draw it nicer. This is 180 degrees. This entire upper part, but the player is located behind the enemy. All right, so this is the other condition here. Let's try one more condition, okay, guys? Just to be sure, I will revert a couple of things, but we will keep it. We'll keep it actually very similar now. Okay, I will just remove until here. I'll remove this part here. Okay, like this. Okay, and I will remove this part of the. Okay, this can actually stay. What I want to change here will be actually how the player is facing. Okay, so I will get this color here. All right, so I will say here my player will be now, the direction of my player will be not facing here, as you can see currently up here, but the player will be facing, the enemy will be facing down here. So it will be detecting whatever is behind it here. Okay, if you want to imagine it in Unity, basically what I would like to do, I would like to set here first of all 180 degrees angle. And I would like to turn the enemy back, so I will just say here rotation of 180 degrees. This will be my rotation angle now. Okay, so I'm detecting whatever is behind the enemy. All right, let's continue with the drawing. Okay, so let me get these tools. So the player normalized position is same, 0.7 minus 0.7. Also, we should revert this. So okay, so the detection range is now the other way around, basically here. So we are detecting whatever is here in the front, this entire part. All right, so now the vector forward of the enemy is not here, because we are not facing the forward this direction, but we are facing the forward down here. Okay, I cannot even mark it here. I cannot hide my panel now, but here. Okay, so now my forward position is what? On the X is 0, but on the Z is -1. So we are looking for a dot product of the normalized of the player. Dot product of the forward in this case is 0 and the -1. So if you want to get it here, dot product will be 0.7 multiplied by 0. It's a 0 minus 0.7 multiplied by -1 is 0.7. Okay. So that's the dot product we are looking for now. And this has to be larger than the cosine of half of the detection angle. So half of the 180 degrees is the 90 degrees. And we already said before cosine of 90 is 0. So this has to be larger than 0, which it is. So this means the player is in the detection range of the enemy. Okay, so conditions are met. And we are definitely in the detection range of the enemy, and you can also see it visually here. Okay, so that's basically how we are computing this position. All right, so we can also, I can show it to you in the code. So not in the code, but in the project, that it will always work, even that we are facing here. I can play the game, and as soon as I will go into detection range of the enemy, I can, where it is seen here. All right, I will go down here. I can see player has been detected. I will go out here. I'm not detected here. I will go actually click here. I will go from this side. I'll go into detection range, and I have been detected. Okay, so we are everything projecting on this unit circle around the enemy, and that's basically how does it work. So you can imagine also here you have this detection range of the enemy. All right, as soon as you are in the detection radius of the enemy, doesn't matter where you are around, you don't need to be exactly in this angle. You can be also inside of this detection circle here. You are basically from this point on, you are projecting the position. I'll just remove it. You are basically projecting the position of the player here. Oops, on this unit circle around the enemy. Oh, I cannot grab my tools here. Okay, so this is a vector to the player position. You are just scaling it down or up on this unit circle. Actual unit circle around the player is much smaller than the radius I'm displaying here, because its radius has a 10 units at least. I will have it somewhere here. When I click on the enemy, you can see the detection radius is at 10 units. And we are projecting it around 1 unit. So 1 unit vector would look like this. That would be 360. So we are projecting this position, since we are normalizing them. All right, so we are normalizing them. So that's the position from the enemy to the player. We are normalizing this, and we are scaling it down. So player position will be scaled down on this circle here. If the player position will be somewhere here, then it would scale it down from here to here, and so on. So that's how it's working. And here is the vector forward, how we are facing. All right, and we are getting this dot product of this position with the forward vector. This will get me some value on the circumference of the circle, and then I will get a half value of the angle where the enemy is facing, and I will compare them together, and this will get me if I am in this detection range or if I am not. Simplified here as I draw it here before on these unit circles and on this grid system. Guys, if you would like to get broader context and more lectures about this stuff, I have a lot of lectures already in my academy.dynco.com, where I'm creating this RPG game step by step, explaining all of this stuff. So you can just simply see all of this here. Also in the introduction video, everything is here. There should be already more lecture included, and you will be creating this RPG game with all of these mechanics and mathematical explanations I try to do in this YouTube video. Of course, it's hard to fit everything in the one video, but I hope you have now basic understanding. Everything we have projected here on the grid can be easily projected also into the game, and that's basically how does it work, how it works. All right, so that should be for the lecture. Again, if you're looking for the implementation, find the link in the description, and all these explanations are also included in my course. And with all of these, guys, I hope to see you in some of my other videos. Cheers.